Okay, let's move on to the second type of aqueous reaction that we're going to get into detail on in this chapter, and these are acid-base neutralization reactions. Now, I mentioned in the overview that an acid-base neutralization reaction involved the reaction of an acid with a base to form water and a salt of some kind. Now, it would probably be worth getting into at this point what an acid and a base actually are. So an acid is a substance that dissociates in water, either completely if it's a strong acid or partially if it's a weak acid, to produce hydrogen cations, H plus ions. So in general, this would be HA, where A is a generic anion, in aqueous solution, splitting apart into H plus and whatever the anion is. So for instance, with a really common acid like hydrochloric acid, HCl, that's a strong acid, so it dissociates completely. And that will split apart into H plus and Cl minus chloride ions. And it's the H plus portion of this that makes it an acid. Now, technically, in aqueous solution, the H plus ions are present as hydronium ions, but that's really not something that you need to know until you get into Chem 1212, so don't worry about this stuff down here. Just know that they dissociate into H plus ions and some sort of anion. And a base is a substance that dissociates in water to produce a different kind of specific ion. For acids, that was H plus. For bases, the characteristic ion is going to be hydroxide, or OH minus. And in general, if we have some generic cation, say M, paired with hydroxide ions in aqueous solution, if we have a strong base, so one that dissociates completely, we'll have some sort of cation, again it doesn't really matter, plus the hydroxide ion, OH minus. And it's this thing right here that causes this to be a base. So if we look at one of our strong bases, sodium hydroxide, in aqueous solution, this will be present as dissociated sodium ions, which don't really affect much, and hydroxide ions, which make this a strong base. Now, when we talked about weak acids and bases, I mentioned that there was one specific weak base that was common, but didn't actually have hydroxide in the formula, and that was ammonia. So ammonia is NH3, and you might look at this and say, how can that be a base? It doesn't have OH anywhere in the formula. There's not even oxygen at all in that compound. And it turns out that ammonia is a weak base because it partially reacts with water, really to a small extent, but meaningfully enough to still be a base, in this reaction that you see here. So the ammonia in aqueous solution partially reacts with the water that it's dissolved in, and it forms ammonium cations, NH4 plus, and hydroxide ions, and again, this is what's responsible for making this a base. This reaction is only a partial reaction, because only a small amount of the ammonia reacts, but we still get some hydroxide ions in aqueous solution, and so ammonia is a weak base. Alright, I showed you earlier on in this presentation, in a previous video, what the strong acids and strong bases were. If you remember what those are, it's pretty easy to deduce that anything else that is an acid or a base should be a weak acid or a weak base if it's not on the canonical lists of strong acids or strong bases. And as the name implies, strong acids and strong bases are strong electrolytes, whereas weak acids and weak bases are weak electrolytes. Okay. And we've talked about how to name acids before, but it's worth recapping this here since we're going to see acids a lot. So if you have an acid that does not contain oxygen, the name starts with hydro. The remaining part of that name ends with the anion name of the acid, but you change the end of the anion name to ic, so generally this can involve changing IDE to ic, and then we have a second separate part of the name that is acid. So for instance with HCl, which is H plus and Cl minus, Cl minus is chloride, If we change that "ide" to an "ic", we get chloric, and since this does not contain oxygen, we put a hydro prefix in front, and we get hydrochloric acid. Same thing goes for hydrobromic acid based on bromide. Hydrofluoric acid, which again is not a strong acid, even though HCl, HBr, and HI are all strong acids. HF, which also contains hydrogen and a halogen, is a weak acid. But F- is fluoride, so this becomes hydrofluoric acid. And then there's a second set of rules for acids that are based on anions that do have oxygen in them. So this does not involve the hydro prefix, and if you have an oxygen-containing anion, the ending of that ion is generally going to be either ITE or ATE. If it's ITE, when you pair this anion with H+, the acid name takes this ite and changes it to OUS, us. So nitrite, pair that with H+, you get nitrous acid. Nitrate, pair that with H+, you get nitric acid. So, like precipitation reactions where we were doing a double replacement process where we essentially swapped the pairing of ions in two different ionic compounds, acid-base neutralizations are kind of like this as well, except the result of the ion pair swapping gives you a salt and water, and specifically the H+ cation and the OH- anion from the base. H+ is from the acid. If you take these two things and you combine them in a 1-to-1 ratio, you get 1 hydrogen plus 1 hydrogen is 2 hydrogens, 1 oxygen, and +1 plus -1 gives you overall no charge, so this is H2O. So this ion and this ion actually kind of come together and form a covalent bond between the oxygen of the hydroxide and the H of the H+, and we get water, which again is a covalent compound, not an ionic compound. And the salt is formed from the cation of the base with the anion of the acid. So whatever the cation from the base is and the anion is from the acid gives you the formula for the salt. Again, you need to take into account what the charge is on the cation and the anion respectively, so that you end up with the correct formula for the salt, and you have to do that before you balance the equation. So let's take a look at an example of a strong acid, strong base neutralization reaction. So we have the strong acid, HBr, hydrobromic acid, and the strong base, barium hydroxide. Those are both on the strong acid and strong base list, respectively, in aqueous solution. Since we have an acid and a base, we know this is going to be a neutralization reaction, so we're going to form water and a salt. H2O, of course, is water, and barium bromide is a salt, so those are mislabeled. I apologize for that. But, of course, H2O is water, and then barium hydroxide is our base, so the cation from this combined with the anion from our acid, so the non-H+ part of our acid, which is Br-, is going to give us the salt, which is barium bromide. Barium is 2+, bromide is -1, so we need 2 bromides for each barium in that salt. So, just like with a precipitation reaction, we need to write down the correct chemical formulas for the reactants and the products before we balance the equation. And so we get that with H2O in BaBr2. Once we have those correct formulas, we can actually proceed to balance the equation. So a good way to know what coefficients you'll need to use is to look at how many hydroxides there are in the base, how many H+ there are in the acid, because those need to combine in equal amounts. HBr has just 1 H+, but barium hydroxide has 2 hydroxides, so we're going to need twice as much HBr as we have barium hydroxides to get the correct amount of water out of that. So we need a 2 in front of HBr. That gives us 2 H+, and now 2 hydroxides from the barium, so we get 2 waters. And with everything else established, we can check to see how many bariums and bromines we have and how many equivalents of the salt that gives us. We have 1 barium, and now 2 times 1 is 2 bromides, so we just have 1 equivalent of BaBr2. Now in terms of states, the acid and the base will both be aqueous. Water is a liquid, because of course it is, and for the salt, we need to use the solubility rules. Now, usually it's the case that the salt that's formed is going to be aqueous, but that's not a hard and fast rule. So barium bromide contains bromide ions. Most compounds with bromide ions, like chloride or iodide, are going to be soluble. There are a handful of exceptions to that, but barium is not one of those exceptions. So since barium bromide is soluble, we're going to keep this as aqueous as opposed to being solid like it would be if we formed an insoluble salt. Now that we have our balanced equation here, and we've assigned all the states correctly, we can use that information to turn this into a total ionic equation where we dissociate all of the strong electrolytes and leave anything else undissociated, and then we can cancel our spectator ions. Now, HBr, again, is a strong acid, and barium hydroxide is a strong base, so those are both strong electrolytes. And we determined that barium bromide was a soluble ionic compound. All salts are ionic, and so that's a strong electrolyte as well. And of course, water, H2O, is a covalent compound, so that is not going to dissociate at all. If we go through and apply all the same rules as before, you should find that both barium and bromide ions are going to be spectator ions. We have 1 dissociated barium on both sides and 2 dissociated bromides on both sides. And so we can cancel those, and that just leaves us with this equation right here. And 2 things to say about this. So first of all, remember when we talked about balancing equations that the last step of balancing any equation is to check to see if the molar ratios can be reduced. And here we have leading coefficients of 2 in front of all of these things, and so we can reduce this down to this bottom equation here. And this bottom equation is maybe somewhat surprisingly simple. We just have H plus in aqueous solution plus 1 hydroxide in aqueous solution gives us 1 equivalent of liquid water. And this net ionic equation right here is actually a really common one. So not all acid-base neutralization reactions reduce to this, but if they meet a certain handful of common criteria, they will. So if we have a strong acid, a strong base, and the salt that's formed is soluble, if and only if all 3 of those criteria are met, the net ionic equation will always reduce down to this thing right here. Now, if any of those 3 conditions is not met, then it's not going to be the case anymore that you'll have that net ionic equation, but it's not uncommon for all 3 of those criteria to be met, in which case the net ionic equation will always be what you see there at the bottom of this slide.